Okay, so here we are in physics class. I'm not here, but Miss Haig is here. Mrs. Haig is here, and she's going to help you do art, and I'm going to help you do physics. So maybe you can get her to help you draw a sprinter in full motion. Okay, other than that, I'm going to continue what we were talking about yesterday. So if you recall, we were looking at velocity time graphs. So if you draw your graph, and this was you know pretty straightforward. We talked about time being on the bottom, and I'll give you a second here to get your notes out. Velocity meters per second. Great. So if you had finished your velocity time graph from yesterday, and we looked at Usain Bolt's 969, right? We can call this sprinter.
This is Dixon, line 1, please.
100 meter.
Dixon, line
Should have been a 100 meter sprinter, but anyway, so when you start at 0, you accelerate at some kind of pace, and then at a certain point you start to taper off and your rate of acceleration slows down, and you see this kind of bend in your curve, and then it kind of levels off and you hit this maximum velocity, right? You call this your Vmax, and you kind of continue at that pace until you kind of got tired and you start to taper off, and that's hopefully going to end up around 10 seconds. Alright, so that's your graph should have looked something like from here all the way to there. Now what we're going to do today is we're going to talk about how we can calculate displacement from this graph. So if you're looking at your graph here, and you can draw another nice line, and they'll meet up nicely there. Good morning, John. How are you today? Good. Velocity again, meters per second, and time in seconds, obviously. So I'm going to just take this graph over here, this guy, and I'm going to make it a little simpler by drawing straight lines. So if I start at 0 again, I'm going to have a constant acceleration. And all I mean by constant acceleration is means velocity increases at the same rate throughout that phase. Okay? So as a straight line just means that your initial V here, we can call this VI, was equal to 0. And then at this time, and we'll call it, say 7 meters per second, that would be your V2 or whatever, your V after this amount of time here, which is, in this case, 1.8 seconds. Let's see if I can move this down. I'm not sure if that's going to be good. Oh yeah, it worked. Awesome. Okay, so then after this constant acceleration phase, we're going to accelerate a little bit more, but not at the same rate. We're going to slow down our rate of acceleration, and it's going to be a little shallower. You notice that the slope of this guy is less than the slope of this guy. Okay, now anyways, so what we do, and we can call this our max velocity again. We'll call this 10 meters per second this time, and then we're going to travel at this pace for a while, and we're going to continue going at that pace. Now this time frame here, this is your second time, we'll call this 3.6 seconds, and then if we travel at this constant pace for 4 seconds, we'd have 3.6 plus 4, so we have 7.6 seconds here. And after that, after you max out your velocity, you start to get tired and you're going to slow down, and it's going to come down here. And let's just say this slows down all the way to 7 meters per second. And what that's going to do is simplify our problem. So there's my final pace. Now when I drop this line down. Hi, Miss Coleman. Yeah, I'm just finishing the video. I'm doing a second take because the first one was a bit messier, so I'll be there in 2 minutes. Okay, so 10 seconds. Yeah, you're right. This is the second time I've tried this. You can watch the more rough video later. I'll have that on there too. Anyways, so yeah, this is our velocity time graph. We want to do the area. Well, why do I want to do the area? I was talking about that yesterday. But if we think about it, this area here, it represents the constant velocity area, right? So at this pace, from here, from t equals 3.6 to t equals 7.6, I'm traveling at 10 meters per second. So how many seconds is this? Yeah, this is 4 seconds. And then if I look at my rectangle here, this is my velocity, which is 10 meters per second. So that comes from the fact that your displacement, okay, delta D, and we'll call this, well, we'll call this color, and I'm going to go back to black here. Let's call this 3, because this one would be 1, this one would be 2, this one's 3, and 4. Now, delta D, and we'll call it 3, we know that this is equal to velocity multiplied by delta t. So my delta t in this case is 4 seconds, and my velocity is 10 meters per second. So delta d3 is equal to 10 meters per second, okay, multiplied by 4 seconds. And there's a bunch of you out there that already know the answer to this problem. It is 40 meters. Okay, your seconds are going to be on the bottom here, and on the top cancels. Okay, so then the next area can be calculated very similarly. So if you look at this, and we'll say, let's call this delta D1. Now if I want to do delta D1, what do I need to do? All I need to realize is that this area can be found by using the what? Yes, you're right, the area of a triangle. So what's the area of a triangle? And base is here, and height is there. So base times height, there you go. Base times height divided by 2, which is equal to, yeah, 1.8 seconds divided by 2, and that's multiplied the base, which is the height actually, is 7 meters per second. Okay, so I have 1.8 times 7, and I need a calculator to do that really quickly, so we'll take 1.8 times 7, and that's equal to 12.6 divided by 2, 6.3 meters. Okay, so he covers 6.3 meters in this first 1.8 seconds. Okay, now if I change color, I can do this guy. But what do you notice about this phase? Okay, delta D2, sorry, we already did 3, is equal to, yeah, the rectangle plus the triangle. Okay, so to calculate this guy, all we have to do is do the first, we have to do this rectangle. So what's the rectangle? It's length times width. It's going to be 1.8 seconds times the height, and the height again is 7, so 7 meters per second, plus this tiny little triangle up here whose base is the same thing as this base here, so it's going to be 1.8. Now the height is going to be 10 minus 7, so this is going to be 3 meters per second, and we divide this one by 2. So you can go ahead and do that on your calculator. You can steal a calculator from the person sitting next to you, or just do it in your head, I guess. 1.8 times 7 gives you 12.6 meters, plus 1.8 times 3 equals 5.4. Divide that by 2, you get 2.7.
That's a lie.
2.7, morning Tyree. 2.7 plus 12.6, and you have 15.3 meters covered in this second phase. So this is your second phase of your 100, where you're still accelerating but not as fast as before. And now I've done the 3, 2, and 1. The final phase I have to calculate for the sprinter is this final phase. And yeah, you're right. In this case, we have a rectangle and a triangle again. This time my rectangle, the base here, or the width you could call it, is equal to 2.4 seconds, and the height of this one is 7. So delta D4 is going to be equal to your rectangle, which is 2.4 times 7, plus your mini triangle, which is going to have a base again of 2.4, times the height of this, so 10 meters per second minus 7, so it's 3 again. And it's an area of a triangle, so you got to divide that by 2. So you got 2.4 times 7. So you have 16.8 meters plus 2.4 times 3. Good morning, Josh. Equals 7.2 divided by 2. You have 3.6. You want to say hi to my grade 11 physics class, guys? They're shy. Yeah, it's recording. Anyways, here we go. 16.8 plus this. Okay, 20.4. The reason I'm doing this is because I'm going across country later, and my physics kids will miss me, so I'm going to be there with them in video. Okay, next. They can't see me, but they can hear me right now. So, well, I'm recording just the screen here. So, anyways, the color I'm going to change back, and let's talk about the total displacement. So, how far did this sprinter go in these 10 seconds? Did he make the whole 100 meters?
No.
We'll see. Tyree thinks not.
He tripped.
I think he just maybe didn't get fast enough. This is probably somebody like me or somebody that's not as fast. Anyway, so we're gonna do this. We're gonna do the total displacement. Your total displacement. All right. Displacement, and we'll do it the sum. And this is kind of cool. Sum is equal to 1 to 4 of delta d n. And this little n, you see this subscript. It's a funny way of writing it, but this little subscript just means that n is going to change from 1 all the way to 4. And you'll see that that's kind of interesting because we have d1, d2, d3, d4. So just add them all up. So we have 6.3 meters plus d2, which was 15.3 meters, plus d3, which is 40. Okay, yeah, go ask her out, guys. 20.4 meters. Morning, Mustafa. How are you today? 6.3 plus 15.3 plus 40 plus 20.4. And this guy made it a whole 82 meters in 10 seconds. So there you go. You've been able to, all we've done to recap, added up the areas, add areas, because the area is equal to displacement. Okay?
Yeah.
And
Counting.
we added different areas. In this case, sometimes there's a triangle and a rectangle, and we added it up, and we found that our sprinter, he's a little slower than a 10-second sprinter because he only made it 82 meters in 10 seconds. So thank you for your time. Hopefully the rest of the class goes well, and have fun enjoying physics. Bye. So